Remember Babcia's pierogi kitchen? Way back in the data lecture? Her direct phone orders averaged about $32, and her app orders about $22. An $11 gap. And we promised that one day we'd be able to say whether that gap was real.
Today is that day. Last lecture built the hypothesis test, one sample against one claim. Today, we point the same machine at two groups at once. Two means, paired measurements, two proportions. Same 4 steps every single time. The only thing that ever changes is the standard error.
This is Week 5, Lecture 17, comparing two groups. Let's settle the $11. So on screen, two groups head-to-head. Direct orders around $32, app orders around $22. And notice the question is not, what's the gap in this week's data? We can see that, it's $11. The question is whether direct is really worth more per order, or whether this particular week just happened to fall that way.
And that changes what the unknown is. Before, the unknown was a single mu. Now it's a difference, mu1 minus mu2, the true direct mean minus the true op mean. So the real question is whether mu1 minus mu2 is genuinely bigger than 0. That's a hypothesis test.
And here's the headline for the whole lecture. It's the same 4-step test as last time. State H-naught versus H-one, pick alpha, standardize, decide. Only the standard error changes. That one sentence carries everything today.
Set the test up before any arithmetic. The parameter is now the difference, so the null says mu1 minus mu2 equals d-naught, some hypothesized gap. The alternative says it doesn't, or one-sided, that it's bigger than d-naught or smaller. And the old discipline still holds. Rejecting H-naught is what backs the claim. We never prove H-naught.
So what is this d-naught? It's the gap the null is willing to grant. Usually it's just 0. The two groups are equal, no difference. But sometimes it isn't. If the claim is material 1 outlasts material 2 by more than 2 units, the null digs in at exactly 2. d-naught equals 2.
For Babcia's kitchen, the claim is that a direct order is worth more than an app order. So H-naught, mu1 minus mu2 equals 0. H-one, mu1 minus mu2 is greater than 0. d-naught is 0, and the test is one-sided.
Here's the map for the whole lecture. 4 tests, 1 template. A difference divided by its standard error. Comparing two means with large samples, it's a z. X bar 1 minus x bar 2 minus d-naught over the root of s1 squared over m1 plus s2 squared over m2. Small samples with equal unknown sigmas, a pooled t, with v equal to m1 plus m2 minus 2.
If the data comes in matched pairs, the same subject measured twice, it's a t on the differences, d bar minus d-naught over sd over root m. And if the data is yes or no in each group, two proportions, it's a z again with a pooled rate inside the standard error.
Your only real job is to pick the row that matches the data. After that, everything is last lecture. The same z or t tails, and every rejection region is still a confidence interval's complement.
Take the first row slowly. With big samples, or known sigmas, the difference of two sample means is itself normal, so we standardize it. Under H-naught, z-naught is x bar 1 minus x bar 2 minus d-naught all over the standard error.
And look closely at that standard error, because it's the one genuinely new thing. The two variances add. Each sample mean wobbles on its own. Each carries its own s squared over m, so the gap between them wobbles by the sum. Root of s1 squared over m1 plus s2 squared over m2. Then reject past z alpha for one-sided or z alpha over 2 for two-sided.
The picture on the right is a familiar friend, the bell with the gold rejection tails and the do not reject middle. Same cutoffs as always. One-sided at alpha 0.05, 1.645, two-sided 1.96.
The moment we've waited 5 weeks for. Setting the $150 catering order aside, the ordinary orders give direct, 19 orders, mean 32.4, S of 9.7, app, 20 orders, mean 21.7, S of 7. H-naught, the channels are equal. H-one, direct is worth more. One-sided, so reject if z-naught beats 1.645. First, the standard error. 9.7 squared over 19 plus 7 squared over 20. Take the root and you get 2.72.
Now z-naught. The observed gap is $10.7 over 2.72. That's 3.92. And 3.92 isn't just past 1.645, it's miles past. The p-value, the chance of a gap this large if the channels were truly equal, is about 4 in 100,000.
Look where the arrow lands in the picture, way out in the tail, far beyond the cutoff. So, reject H-naught. Direct orders really are worth more per order. The $11 gap is real. Question asked in week 3, answered in week 5.
Now shrink the samples. Small samples, sigma unknown. Last lecture, that combination took us from z to t, and it does again here. But with 2 small samples in one shared spread, we get to pool one combined variance, sp squared, m1 minus 1 times s1 squared plus m2 minus 1 times s2 squared over m1 plus m2 minus 2. Then the statistic is the same template, the difference minus d-naught over sp times root of 1 over m1 plus 1 over m2, with v equal to m1 plus m2 minus 2.
Why pool at all? Because assuming sigma 1 equals sigma 2 means both samples are estimating the same spread, so let them chip in together. It's a weighted average of s1 squared and s2 squared, weighted by degrees of freedom. And if the two spreads clearly differ, you just skip the pooling. There's an unequal variance form. Same idea, adjusted v.
And notice the little bonus in v. m1 plus m2 minus 2 is 2 more degrees of freedom than a one sample t would give you at the same total size. Both samples chip in their spread.
Let's run one where the null grants a head start. 2 materials, depth of wear. Material 1, 12 pieces, mean 85, S of 4. Material 2, 10 pieces, mean 81, S of 5. The claim, material 1 wears more than 2 units deeper, so d-naught is 2. H-naught says the gap is exactly 2, H-one says it's bigger. Equal variances, alpha 0.05, and v is 12 plus 10 minus 2, 20. Pool the spreads, 11 times 16 plus 9 times 25 over 20, 401 over 20, 20.05, so SP is 4.48.
Now t-naught, the observed gap is 4. The null already grants 2, so the numerator is just 2. The denominator, 4.48 times root of 1/12 plus 1/10, 1.92, so t-naught is 1.04. The cutoff, t at 0.05 with 20 degrees of freedom, is 1.725, and 1.04 doesn't come close. The p-value is about 0.15.
The picture says it kindly. The arrow parks in the middle of the curve, nowhere near the gold tail. Do not reject. Material 1 does wear more, but more than 2 units more? The data can't back that.
Now a twist in the design of the data. Sometimes the 2 samples aren't 2 separate groups at all. They're the same subjects, measured twice, before and after a treatment. Twin against twin, left against right. Then compare within each subject. For each pair, form one difference, di, first measurement minus second. And the whole 2-sample problem collapses into a 1-sample t-test on those differences. T-naught is d bar minus d-naught over sd over root m, with v equal to m minus 1.
The picture shows why that's worth doing. Top panel, 2 independent clouds, and the spread from subject to subject nearly buries any shift between the groups. Bottom panel, the same idea as matched pairs, one gold link connecting each subject's first and second measurement.
Each gold link is 1 di, and that's the trick. A subject who runs high is high in both measurements, so the difference wipes their personal level out entirely. Pairing cancels subject-to-subject noise. What's left is just the shift you actually care about.
The classic paired setup. 15 deer, androgen level measured at injection, and again 30 minutes later. Same animal, 2 moments. That's paired. Did the level change? Two-sided, alpha 0.05. V is 14. From the 15 paired differences, D bar is 9.85 and SD is 18.47.
So t-naught, 9.85 over 18.47 over root 15, that's 9.85 over 4.77, 2.06. The two-sided cutoff at v equals 14 is 2.145, and 2.06 sits just inside it.
The p-value, twice the tail past 2.06, comes out about 0.058, just over alpha.
Look how close that arrow sits to the boundary line. The verdict is do not reject, but barely. And that deserves a beat. This close to the line, a slightly larger sample could flip it. Do not reject is not the same as no effect.
Last member of the family, yes or no data in each group. 2 approval rates, 2 click rates, 2 support rates. Under H-naught, the 2 true proportions are equal, so the best single estimate of that shared rate simply stacks both samples. P-hat is x1 plus x2 over m1 plus m2, and Q-hat is 1 minus P-hat. Then z-naught standardizes the gap between the sample rates, P-hat 1 minus P-hat 2 over root of P-hat times Q-hat times 1 over m1 plus 1 over m2.
Why the pooled rate inside the standard error? Because the null says the rates are equal. So while we're testing that claim, the honest standard error uses the one shared rate, not the 2 separate ones. The tails are the usual z-tails, past z alpha one-sided, z alpha over 2 two-sided.
One health warning at the bottom of the slide. This is a large sample tool. You want at least about 5 yeses and 5 nos in each group before the normal shape can be trusted.
A proposed chemical plant and a vote. In town, 120 of 200 voters in favor, 60%. In the surrounding county, 240 of 500, 48%. 12 points apart. Is town support genuinely higher, or is that sampling noise? Alpha, not 0.05. H-naught says the rates are equal. H-one says town is higher. Pool the rates. 120 plus 240 is 360 over 700, not 0.514.
The standard error, root of 0.514 times 0.486 times 1 over 200 plus 1 over 500, 0.042. So z-naught is the 12-point gap, 0.12 over 0.042, 2.87, well past 1.645, and the p-value, the tail past 2.87, is 0.0021.
And the arrow lands solidly in the gold tail. Reject H-naught. The town support really is higher than a county's. A p-value of 2 in 1,000 says not sampling luck.
And as always in this course, the test and the confidence interval are 2 views of one calculation. Now for the difference. The interval, x bar 1 minus x bar 2 plus or minus t alpha over 2 times sp times root of 1 over m1 plus 1 over m2. Large samples, same thing with z alpha over 2 and the added variance is standard error. And the link is exact. You reject H-naught precisely when d-naught falls outside the interval. The little t table on the right is full of old friends. The v equals 14 row is the androgen test. The v equals 20 row is the abrasive wear. Same rows whether you're testing or building the interval. So you can read any difference interval as a verdict. A 0 inside the interval means no detectable difference. A 0 outside means the gap is real. It's the test written in interval form.
And if tables aren't your thing, GeoGebra's free probability calculator has a statistics tab that runs the whole lecture for you. Pick 2-sample t-test or the z version. Type in each group's summary, the mean, the s, the sample size. Choose which way the alternative points, and it hands back t-naught and the p-value directly. What's on screen is our abrasive wear example. T-naught 1.04, p about 0.15, the same do not reject we found by hand. And a 2-proportion test reproduces the vote too. Z-naught 2.87, p 0.0021. Use it to check your handwork, not to skip it.
So what we built today, 1 test, 4 standard errors, the 2-sample z and the pooled t for comparing means, the paired t for matched subjects, the 2-proportion z for comparing rates. Every one of them is a difference over its standard error, and everyone is still a confidence interval's complement. And Babcia answered. The $11 direct versus app gap gave z-naught of 3.92, far past 1.645, with a p-value of about 4 in 100,000. The question we've carried since the data lecture finally has its verdict. The gap is real.
Next time is the last teaching class of the course, simple linear regression, fitting a straight line through a cloud of points so that one measurement can predict another. See you there.